ஒருவேளை பண்ணிட்டோம்
So, good morning, students. We will continue on the topic of regular languages. So, in yesterday's class, we looked at how to draw the transition diagram. I mean, the automaton with respect to some of the regular language definitions. So today, we will look at another kind of automaton, which is called as non-deterministic automaton, or it's called non-deterministic finite acceptor. So you have the complementarities, which is the deterministic finite acceptors, and here you have non-deterministic finite acceptors. Right? So now, why do we call DFA DFA? Because, or why do you call a DFA as a deterministic automaton? The reason being that with respect to DFA, you have a unique transition. So for each state and input number. So we saw that we had the states here and we had the inputs here, right? So we have the states here, we have the inputs here, and with respect to every input, there was only one unique state to which this transition would occur to, right? So now there was not more than one state. Right? So with respect to every with respect to every state transition. So now, with respect to every input, like we can do this kind of I mean, we have this kind of a transition with respect to DF. Right? So now, this is what we studied. We studied that delta is the total function. Right? So this unit transition defined for each state and each input symbol formally was expressed by saying that delta is the total function. Right? So that's the reason why you call the automata deterministic, right? So now you have the counterpart who is non-deterministic automata. Can you please mute Samartha? So now now uh, we also know that computers are deterministic, right? So, but still, we because computers don't take non-deterministic action. So, what is non-deterministic action? So, when we say like from one particular state, maybe with some probability you may go to another state, and with some probability you may go to another state on the same input, right? Then we call this kind of a system which is going to act in this fashion as non-deterministic system, right? So, but we know that in general, like computers are just going to do whatever that is being told to them. So you have your instructions, and you have 10 instructions. Computer is just going to execute these 10 instructions and then halt, right? So that is what a computer is going to do, right? So computers are deterministic machines, right? But non-determinism comes into application in some places. And for the theoretical understanding, we study non-determinism. Right? So now, how do you define a non-deterministic acceptor? Right? So non-deterministic so basically, what I told is when we say non-determinism, it means that there is a choice of move, right? So choice of moves for an automaton. So automaton can make a choice rather than having only unique move for every state. You allow a set of moves, right? So now it means going to be a change in the transition function. So for a non-deterministic automaton, it is also defined by kin tuple, which is 5 tuples. So it is defined by this 5 tuple that is given by Q, sigma, delta, Q naught, and F. Okay, so these are the 5 tuples that are going to define the non-determinism, right? So non-deterministic finite-state automaton. So now, with respect to delta, there is a change. So delta is defined as a function that goes from Q to sigma union lambda. I mean Q cross sigma union lambda to 2 power, right? So this is how you define a non-deterministic automata. So the transition is defined from one particular state to, one particular state on some input symbols. So these are the input symbols, right? And this is the current to a set of states. So now the range here can be a subset of this power set of Q, right? So now you can go from say Q naught Q2 may be like Q1 or Q3 on the input A, right? So a single transition delta. Now, how do you define? So you define delta as from Q0 on input A as going to Q1, Q3. So now this is going to be a subset of the power set of Q, right? So that's how like you define. So this is going to be the set of power set of Q, right? So that's how you define the non-deterministic, right? So basically there are three um, differences. The first difference from with respect to a deterministic finite acceptor is that the range for delta is in the power set of in the power set to power q or power set of q, right? So to power q, right? So this is the first one, right? Now we also see the second difference, which is that we allow lambda as the end argument of delta, right? So here you also see lambda here, right? So in the earlier case, we saw that with respect to a deterministic finite state automata, you had q cross sigma gives q, right? So this was the transition function with respect to a deterministic finite state automata. Now, with respect to a non-deterministic finite state automata, we find that we have included lambda. It means that a string of length 0 also as one of the inputs in the non-deterministic finite state automata. Right? So it means that from a state Q0, you may, if there is a lambda transition that is defined, it means that from Q0, you may reach Q1 without consuming any input, without consuming any input, right? So you may be able to go from this state to this state without consuming any input, right? So that is what we define by this second difference, right? Now the third difference is that you can allow for delta of qi comma a to be empty, right? So it means that there can be no transition that is defined for a specific situation. Now, we saw that with respect to a deterministic finite state automata, we had the state, we had the inputs, right? Now, the state transition was defined with respect to every input. For all input, there was a state transition from any state. Now, here you can allow for delta qi comma a being the input symbol, qi being a current state, be empty. It means that you can have some state transitions which are not defined at all. So you can allow for some of these state transitions that are not defined at all, right? So you have these three differences with respect to a deterministic finite state automata, right? So now a string that is accepted by a non-deterministic finite state automata. When you say a string is accepted by a non-deterministic finite state automata, at the end of the string, so how does our machine work? You have an input tape, right? So on the input tape, you have the string. So let's assume like you have A, B or something, right? Now this is present on the input tape, right? Now you have a read head, right? And then you have a control unit, right? And in the control unit, you have the state transition, right? And in the state transition, you have some state and the state, and you have some state that is defined as the final state, right? Now, as you read the input symbol, you have state transitions that happen within the control unit. By the time you read, let us assume the last symbol is specified by a dollar or something. Right? By the time you read the last symbol, you check the control unit checks whether the automata is in final state or not. If the automata is in final state, then it says that the string belongs to the language. If the automata is in a non-final state, then it says that the string does not belong to the language. So this is going to be your automata. Right? So this is your automata, or this is your computer. Right? So now the automata is basically going to be placed within the control unit. Right? So the automata at any time it doesn't have any other memory like a stack or queue, nothing is there. It just remembers only one thing, which is the current state. Right? So this is one model of a computer. Right? So this is one simple model of a computer. Right? So now in the same way, now if you can replace this finite state automata or deterministic finite state automata by a non-deterministic finite state automata or n of it. Right? So now if you replace by non-deterministic finite state automata, then in this automata you're going to have these three extra properties. It means that you can have the range delta that is in the power set of Q. You can allow for lambda transition. You allow for a transition not to be defined at all. Right? So you can allow for these three things. Right? Now, let's look at one example. So let's look at a transition. So we have Q naught and Q1 and Q2. So we have this. So the transition is on the input. So now what's the language that is going to I mean, what language is it going to specify? What is the language? What are the set of strings of this language? What are the strings of this language? So anybody can answer?
Sir, A,
A,
yes,
then
and A
A,
times A,
4 times A,
and so
and so
on.
on. These are the strings of this language. Now, this is a N of A or a D of A.
NFA, sir.
By virtue of this property that we are having the range of delta in the power set of Q, this is a N of A. Right? Because on a single input symbol, you have two transitions. Right? So if delta is defined for A, from Q0, you need to have both Q1 and Q4. Right? So delta for Q0 comma A is going to be Q1 comma. So by virtue of this, we can say that this is the now now we may have a transition diagram like this, where you know, so um, the here like what are the strings of this language? What are the strings of the language?
1 0.
Is there anything before that?
Lambda.
Okay. So then we have 1 0, 1 0, 1 0. Then then it's all going to be 1 0, 1 0 concatenation, right? So 1 0 1 0 or 1 0. So this is going to be the sequence of things. Now, can lambda be the string of the language defined by the CFA?
So if the initial state is the final state, then yes.
I mean, so this just as binary answer. So the answer is yes. Okay. So now yes. So with the condition that the initial state is the final state. Right? Now here we have this is a DFA or NFA. We call this NFA because there is a lambda transition, right? So because the lambda transition has been defined, you have an input as lambda. You call this as a NFA. So now similarly, like if you extend the definition of a walk, right? Say, if you give the second argument of delta a string, right? So then you have a star here, right? So delta star qi comma w is going to be defined by q capital Qj, right? So so in the DFA, how did we define? We define delta star qi comma w is equal to sum Qj, right? So this is with respect to a DFA. With respect to N of A, define it by capital Qj. Right? So what is this capital Qj? This capital Qj is the set of all possible states the automaton may be in. Right? Having started in Qi and having read W. Right? So if you take this particular example of this month, say um, what is the, if you take this example, delta star Q naught comma A A, right? So what is this going to be? This is going to be on reading A, you may be either in Q2, so you can have Q2, or you can also be in Q5.
Q5.
So this is what is going to be the resulting state after reading to A. Right? So that way we can write that from Qi on reading W, you can be in the set of all possible states. The automaton may be in having started in Q and having read W. Right? So now um, we can define this extended transition function. This you call as a extended transition. So it's defined as the Qj. I mean, it's going to contain Qj if and only if there is a walk in the transition graph from Qi to Qj labeled. Uh, so a state Qj is uh, will be in an extended transition function delta star Qi comma W if and only if there is a walk in the transition graph from Qi to Qj labeled W. Now let's look at another diagram. So you not and you have Q, lambda, so E. So you have this so what about delta star Q1 comma A? So now as we already defined it here, right, on you define lambda as an input where there is a transition without reading any input symbol, right? So now in this case, I go from Q0 to Q1 on input symbol A, right? So here I am asking for an extended transition function from Q1. Now from Q1 on no input I go to Q2. So without any input I can go to Q2. From Q2 without any input I can go to Q0. Now on input A I will go from Q1. Sorry, Q on without any input I go to Q1. So now since here we are asking for an input A, so what we need to see first of all from Q1 without any input. So what is A? A is this going to be, we can have many number of lambdas here and A here, and you can have many number of lambdas here. So this is also equal to A, right? So you can concatenate with strings of length 0 on either side, and still it's going to be A only, right? So from Q1, I may go to Q2, Q0, and then to Q1 on reading input symbol A, right? So I write it as, and after A also I have several lambdas, so I will be still able to go to Q2 and also Q0, right? So if you assume this string as A followed by many lambdas, then what we can write this as, from Q1 on reading input symbol A, I go to Q1 itself, right? And then since there are lambdas following A, I will be still able to go to Q2 and also Q0, right? So I can write this as Q1, Q2, Q0. Are you able to follow this? Now let's look at another thing. Delta star Q2 comma lambda, right? So Q2 on lambda input, I will be able to go to, let's look at Q2 on lambda. So where will I be able to go to? I will be able to go to Q0, right? So without any, on a input of string of length 0 from Q2, I will be able to go to Q0, right? So further I will not be able to move, right? So now delta star Q1 comma lambda. This is going to be, I can go to Q2 and also Q0, right? Similarly, if I have delta star Q2 comma A, A, right? So now where I'll be able to go? So Q2 comma A. So first I'll go to Q1 back to Q2. Then second I'll go to Q1. So on these two inputs, is this equal to, this is equal to having on reading 2 times A, where all I will be able to reach? I'll be able to reach, say, uh, Q1, I'll be able to reach Q2, and I'll be able to reach Q0. Are you able to follow this?
Yes, sir.
Right? So it's like from Q2, without any input, I'll be able to go to Q1, and then once more, without any input, I'll be able to reach Q0, right? With only one A, I will be able to come to Q1, right? Then once more, without any input, I'll be able to go to Q2 and also to Q0, right? Now with 2 A's also, I'll be able to come back, right? And after reaching Q1, I'll be still able to go to Q2, I'll be still able to go to Q0, right? So that's why, like, we have the transition that is defined in this kind of a fashion, right? So this basically means that say having multiple, maybe 2 lambdas from Q2, maybe I have 1 lambda and then a, then maybe lambda, lambda A, then lambda lambda, right? If all the states that are reachable and with one lambda after A, two lambdas after A, several lambdas after A, all that like I'll be able to write here, right? So this way like we compute the lambda transitions, computation of lambda transition. So now so the language accepted by NF. So the language accepted by the NFA is defined as the set of all strings accepted by. So now, uh, um, if for a string W, right? So with respect to NFA, we will see that if there is a string, you may have reached a set of states after reading this string, which may include non-final states as well as final state, right? If on reading an input string W, if the NFA reaches at least one final state, then we say that the string is accepted by the NFA, right? So you have a set of states that are defined as the final state that is defined in the symbol F, right? The set of all states that are reached after reading the input symbol, if there is an intersection, if the intersection between the set of all states that are reached by the NFA and the final state, and if this is non-empty, then we say that the string W is accepted by the NFA, right? You have a set of states which are defined as the final states. You have a set of states that are reachable by the NFA after reading the symbol W or reading the string W, right? Now you take the intersection of these two, right? So these are the reachable states after reading string W, right? And you take the intersection of these reachable states as well as the set of final states. And if this is not equal to empty, then we say that string W is accepted by the NF, right? So that is what we say, right? So now we can define it in this fashion, that the language L accepted by an NFA M equal to Q comma sigma comma delta comma Q naught comma F is defined as the set of all strings accepted such that L of M is equal to W belongs to sigma star such that delta star Q naught comma W intersection F not equal to null, right? So we say that this language is going to have a set of strings W that belongs to sigma star such that you have an extended transition from Q naught, right? And this is going to give you, we saw it's going to give you Qj, right? So in the earlier definition, like we saw that we are going to have Qj, right? So yeah, here we saw that with respect to NFA, you are going to have capital Qj, right? So now this Qj intersection F should be a non-empty set. Then W is going to belong to the language that is accepted by a NF. Right? So this is how we define um, uh, 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 define the language that is accepted by the NF. Right? Now let's look at this particular example. So, this example. So in this example, what's going to happen if we present it with a string that is W equal to 110, right? So we are presenting with 110. Right? So we know that the language is going to be, the language is accepted by this automaton is going to be 10 the power n, right? So where n greater than or equal to 0. So this is going to be the language that is that defines this automaton, right? So if we give 110, so what is going to happen? We are having a transition from Q0 to Q1 on input 1, from Q1 to Q2 on input 1. Then you don't have any transitions that are defined for another 0, right? So that you call as a, I mean, with respect to NFA, you may have this kind of non-definitions, because according to the definition of NFA, we have this thing that delta Qi comma A can be empty, right? So it means that Q2 need not be defined, I mean, transition from Q2 need not be defined for all inputs, right? But with respect to a DFA, with respect to every state, like we define the transition for every input, right? So from Q2, we have not defined any transition. So it is a undefined transition. So such a situation, you call it a dead configuration, right? So it means that it's a kind of a, so by virtue of dead configuration, we say that this string does not belong to the language, right? So it means that the automaton will delta transition, delta from Q0 comma 110 is going to be an empty set, right? So we say that this string is not accepted. Now, now we find why do we study non-deterministic? There are a few reasons that are given in your text. So the reason, first of all, like digital computers are completely deterministic, right? So when we say that digital computers are completely uh, deterministic, what we mean is that you are able to predict their states based on the current state and input at any time, right? So if you know the current state and the input, then obviously like you'll be able to say um, uh, uh, what the next state, right? But what are we trying to do we are trying to model some systems. I mean, we are by introducing this thing of non-determinism, you are trying to model kind of systems which include non-mechanical features, right? So any mechanical feature, any mechanical device is not going to have this kind of non-determinism, right? By design, I mean by design. Of course, a mechanical device can always fail. That is a different thing. But by design, it is not going to have this kind of random behavior, right? So this you call this it as a non-mechanical feature, right? So then, like, why do we study this kind of systems? But okay, mechanical feature, mechanical device system may not have this kind of randomness, right? But then there can be programs which have this kind of behavior. Right? So the maybe a game playing program or maybe any real time program may have to be written for some kind of an eventuality. So it's going to have non-deterministic behavior. So when such kind of programs exist, it means you have a choice and you make one choice and you leave the other choice, right? So now now if we are going to have such programs, then obviously you need to make the best choice, right? So now why do we need to have the best choice? So that you don't have to backtrack, right? So or if you don't want to have any backtrack, at least you should have minimal backtrack. So if you want to represent such algorithms or if you want to model such algorithms, then obviously like you need to go for these kind of non-deterministic automation. Right? So you need to introduce, you need to have those algorithms modeled using these kind of non-deterministic machines. Right? So that is why that is one of the reasons you have the non-deterministic. Right? So so also there are some languages, right? Say you may have a language where you may have a choice, right? Say for instance, earlier in the beginning class we studied about grammar, right? So, with respect to grammar, like if you have a non-terminal, you may be able to replace this non-terminal by say either S may be replaced by ASB or you may replace it by lambda, right? So now it means that you have a choice, right? So in order to describe such kind of, I mean, so there may be languages which involve these kind of choices. This is a grammar. So grammar is also another way to describe a language. So now when you describe a language using a grammar, then also there can be some choices that are involved. And non-determinism basically describes such complicated language which involve these kind of choices. Right? So that is also another reason for introducing non-determinism. The third reason is that this is the first reason because it allows for backtracking and or you can model algorithms like which involve backtracking. And the reason is that there are complicated languages whose grammar involve choices, right? In order to represent such kind of languages, you need non-determinism. The third reason is that there are some results which are easily established for a NFA than a DFA, right? So some theoretical results are easily established for NFA than DFA. So, so also like you introduce these kind of non-deterministic machines. Right? So now, if you ask like, okay, so basically, like I'll just try to put in the theme. So we are trying to describe languages, right? So this was our original objective, right? So languages basically means you are going to have a set of strings, right? Now DFA is a kind of automaton which may be able to describe some type of languages, right? Now NFA is also a kind of automaton that is used to describe some type of languages. But NFA is in no way better than a DFA in the sense that you will, whatever set of languages that is defined by a NFA can also be defined by a DFA, right? By virtue of defining some languages by a NFA, you don't have any advantage. It means that if this is the set of languages that can be defined by a NFA, the same set of languages can be defined also by a DFA, and you can have an equivalent DFA for any NFA, right? So I have a language, I have a NFA for this language. Now I can always have a DFA for that language, right? I have a language. Language is basically a set of strings, right? Now this set of strings is defined by this NFA. Then surely I can define the same. I can convert this NFA into a DFA also, right? So in the coming classes, like we will be looking at this kind of aspects, right? So about like how to define language by NFA and DFA, as well as how this particular property of equivalence between a NFA and a DFA is established, right? So when are they going to be equivalent? If they are going to um, describe the same language. You have language L and you have uh, D1, which is the DFA that describes this language. Now you have N1, which describes the same language L. Then we say that these two are going to be equivalent, right? So now the same set of strings that are accepted by this DFA should also be accepted by this NFA. Any other string should not be accepted by this DFA, and the same should be valid for the NFA also. Then we say that this NFA and DFA are equivalent. So we will study about okay. Okay. So thanks a lot. If you have any queries, you can just ask. Okay. Thank you.
Thank you, sir.